Okay, so we want to know where is 3 times the tangent of pi over 4 quantity squared equal to 1? Well, the idea is again the same. Let's get the tan of theta over 4 by itself. So we need to divide both sides by 3 to get tan squared theta over 4 equals 1 over 3. And then let's take the square root of both sides to get tan of theta over 4 equals 1 over the square root of 3, which you should recognize as root 3 over 3 when you rationalize it. Well, what's going on here? First off, this should be plus or minus because we took a square root. But what's going on here? We have theta over 4. We have a modified period. That is a little bit of a problem. How do we handle this? Well, let's again make an algebraic substitution. Let's say let x equal theta over 4. And then we can think of this as tangent of x equals plus or minus root 3 over 3. And that's easier for me to think about than that weird theta over 4 thing. So, draw yourself a unit circle. Tangent only really has a few different values that it goes through. At pi over 4, it is positive 1 because the x and y values are the same, and tangent is equivalent to thinking of slope. When it's straight up or down, tangent's undefined, and when it's a straight horizontal, so at 0 or pi, it's 0 because it's the slope. So what about the pi over 6 and the pi over 3 values? So I remember that for both of these values, tangent is either the square root of 3 over 3 or the square root of 3. That's cool because then think about which of these two lines is steeper. The steeper line will be root 3 and the more shallow line will be root 3 divided by 3. It's got to be a smaller number. So we need to be looking at that line right there, which corresponds to pi over 6. And equivalently, it corresponds to 7 pi over 6. That's the same line. They have the same slope. Therefore, both of those values will give us a positive root 3 over 3. And then we need the corresponding negative values as well. But again, it's coming down to symmetry. And it's going to be these two values as well, 5 pi over 6 and 11 pi over 6. But we have a problem. Those are the x values that give us root 3 over 3, and we need the theta values. So we need to think about what is theta with respect to x. So we know that if x is a solution, pi over 6 being an x, these are all x values. Let's convert them to theta values because we know that x equals theta over 4. That means that theta equals 4x. Okay. But remember, we're restricted to the domain of 0 to 2 pi. So if we're dealing with values that go greater than 2 pi, which is highly likely here since we're multiplying them, then we cannot accept those as solutions. So let's think about what theta values we get. Well, what about pi over 6? If we take our x value of pi over 6 and multiply it by 4, is that still in our domain? Well, yeah, 4 pi over 6 simplifies down to 2 pi over 3. Think about where that is. That's this value right there. So that's certainly in our domain. So that's one solution. We've got theta equals 2 pi over 3. Cool. Well, let's think about our next smallest theta value, 5 pi over 6. If we have 5 pi over 6 as an x value, and we multiply that by 4, we're going to get 20 pi over 6, which will reduce to 10 pi over 3. And then you have to think about the question, is 10 pi over 3 greater than 2 pi? Well, let's check. Let's give it a denominator of 3, which means we need to multiply by 3 in the top as well. So 6 pi over 3 is the same. And now we can see 10 pi over 3 is greater than 6 pi over 3. So that means that that can't be a solution because we'll be more than one full revolution, which means that 7 pi can't either over 6, and nor can 11 pi over 6. So we actually only have one solution, 2 pi over 3, and that's because we've restricted our solutions to the domain of 0 to 2 pi. Kind of tricky, but hopefully you can follow the arguments here.